Hey everyone, let's talk about the idea of an impedance versus an admittance matrix. This is going to be our first introduction to microwave network theory or network analysis. So up to this point, we've basically been describing and practicing and solving problems with what you might call a one-port network. Okay, so that's an important term, one-port network. Okay, so for example, what would a one-port network look like? Well, you start with something like a transmission line, like so, and we'll draw this out. And at the end of that transmission line, there might be a load, which we'll denote with a load impedance Z sub L. Right? And the definition for that load impedance, first you would have to define some kind of reference plane here. So I'm going to call that Z equals 0. So that Z represents position and not impedance. And we would define the impedance, the complex impedance at that location at Z equals 0 was, by definition, so you do the little triple bar here, it was the ratio of the voltage at that location relative to the current. So the voltage divided by the current at this particular location in space was defined as an impedance. So I put little tildes over here to remind you that these are complex values. Now it's also important to remember that this load here is kind of arbitrary. It might be something as simple as a resistor or an open circuit. It could be a complex circuit with a bunch of resistors and capacitors and inductors and antennas all bundled together. Or it could even be resistors and capacitors and transistors plus a length of transmission line, right? So what it really helps to do is imagine, instead of this little lumped element, I'm going to take a more black box approach, like so. Okay, and this would be my network here, which is kind of a fancy word for just this bundle of circuit components. And somewhere here, I have to again define my reference plane here as the input to this little network here. And so that has a name. That's called a terminal plane. Okay, it's an important idea that will come up from time to time. And you can think of that as just the reference for where Z equals 0 is going to be, right? Because if I slide this back and forth, I still get some impedance, and I could hypothetically include that length of transmission line into this black box here. So this notion here, terminal plane, and we tend to denote it with a T here, which is going to be useful when we get into more complex networks. Now, it's also important to remember that these voltages and currents consist of forward and reverse propagating signals. So I'm going to write V of, I'll just say of 0 here, but this could hypothetically be a function of Z, was some positive voltage evaluated at 0 plus this negative propagating voltage. So these were these waves that would either propagate forward and reverse. And likewise, I had my current here was some I plus evaluated at this position. And this could again be a function of Z. And then we said minus the reverse propagating current here. Okay, so this idea of forward and reverse propagation will be important a little bit later when we start doing scattering theory. But for now, we're just going to focus on just the total voltage and current as a way of defining the impedance at a particular location along some complex circuit. So that should be pretty straightforward in terms of what a one-port network is all about, right? I just have some complicated circuit here inside of a black box, and there's a voltage and a current feeding into this thing. So there's a forward and reverse propagating wave here and with a voltage and current associated with it, which allowed me to define this impedance. But let's go and make things a little more complicated. So I'm going to just kind of draw another black box over here, like so. So here's some black box. I don't know what's inside of it. I just know it's a black box and there's a bunch of sophisticated things buried inside of here. And there's a bunch of input and output ports on it. So maybe there's an input and out. So there's a port here, right? So by port, we mean a positive and a negative reference here. Okay, so it could be like a single coaxial cable plugging into it, like a little BNC cable. And there might be another, port over here with some positive negative reference, so another little connector, and maybe another one over here, like so, and maybe there's even, and I could do this n times, right? So I could call this, say, V1, V2, and there'd be a corresponding current, I2, V3, dot, 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 all the way out to V sub n. Okay? So you would call this an EndPort network. Okay, so just as we had this one port network, which was just a single in with a single connector here, and now I have an EndPort network. So you can think of each port as basically just one of these, right? Just a connector here with a inner conductor and a negative reference to it. And if I have a black box, I could arbitrarily have n of these things sticking out of it. And maybe they all interact with each other. Maybe they're all completely isolated. Who knows? And we're going to just use sort of a mathematical formalism to describe all of those various situations. So what you then have to do on something like this is I'm going to define little reference planes here. So I'm going to call this T1. Right here is T2. This is maybe T3 all the way out to T sub n. And these are called the terminal planes. And again, these just are how you would define sort of a zero phase reference with respect to that little port. Okay, so what would an example of something like this maybe look like? Well, a very, very simple one. Maybe you've seen these. I wish I had an example. Unfortunately, I checked and I don't. But maybe you've seen the T junction for a B and C connector. So it'll look something kind of like this. So it's just a little B and C connector where a cable comes in and I can have two little cables going out. So you would call that the T junction, like so. And who knows what's inside of it? Maybe there's some complicated circuit inside of it. Maybe there's a bunch of resistors and capacitors, or maybe it's just wires connecting and splitting apart here. So I would have, some voltage 1 and a current 1 over here. And for reference, it helps to remind ourselves that these are complex phasors, but we're not really going to be doing anything in the time domain for a while, so I'm going to probably start dropping that tilde convention. And there'll be a V2 and an I2 over here, and a V3, comma, I3 over here. Okay, so the idea is if I feed, say, some voltage or current into this port, you might get some voltage and current coming out of the other two. And vice versa. I could feed some signal into here and it'll split around in some interesting way out the other two ports. So what does it mean to speak of impedance in this sense here? Because I could have a voltage here exciting a current over here and vice versa. So you have this sort of cross-talking between all the ports in your network. And I want to be able to describe that in some sort of interesting mathematical formalism. So what we do is we create what is called an impedance matrix. So it's going to look like this. Impedance matrix. And the way we would write it out is you imagine my three voltages, V1, V2, V3. And these are all phasors. So don't get the impression that just because there's no little tilde here that they're time domain. We will not be doing anything in time domain for a long time. So everything is now officially in the phasor domain. I'm going to write something like this. Z11, Z12, Z13, like so. And then Z21, Z22, Z23, then Z31, Z32, Z33, times my current here, I1, I2, I3. So you notice I've taken this notion of impedance and sort of spread it out a bit in a way that allows me to speak about how voltage here will create current over there. Because remember, at the end of the day, impedance is defined essentially as a ratio of voltage to current, but there's no real reason why those voltages and currents have to be at the same point in space. You can think of this in terms of a cross impedance where the voltage over here creates a current over there, and so I can define an impedance associated with that phenomenon. So obviously this is going to be a lot of work if I have, say, 50 ports here to write out a 50 by 50 matrix and 50 vectors. So we need a new notation to save ourselves from having to write out this gobbledygook. So I'm going to call this a vector V, which I will denote with a little arrow here. And over here, this is going to be the matrix Z, which I will denote with a double bar. And then I have the current over here, which I will denote with as a vector, a column vector, using a little arrow there above it. Okay, so normally what happens is with matrix vector notation. You usually reserve vectors for little boldface letters like a little v, but you can see the difference between a capital V and a little v is kind of hard to to write out with handwriting. And we would then use the capital Z and then a lowercase I like that. But that's kind of a cumbersome notation. We can't do bold font with pencil and paper really. So if you see the little arrow here, remember that implies a vector, the double bar is a matrix, and then the little arrow again is another vector. So hopefully that notation should be fairly intuitive. So rather than write out this big giant, matrix vector thing, I'm just going to write this as the following. I'm going to say the vector v is equal to z times I, like that. So this is a matrix vector equation designed to encapsulate all of this information. So, well, how is that interesting? Well, we also have what I can do is invert this matrix. So I could say z inverse times v is equal to I. And this thing here also has a name. It is called the admittance matrix. I'm going to give it a y with a double bar, like so. V is equal to I. So, or equivalently, we'll just put it over here. I'll say y v is equal to I. So these are the two equations that are going to be interesting to us for the next section. So, okay, so this is the impedance matrix here, represented by all these terms. And then alternatively, the inverse of that gives me the admittance matrix, which would also have a similar form of this, just with little y's instead of z's.